Oh, hi everyone. Thank you for organizing this. It's I would have preferred to be there in person, and I realize with the time differences, most of the talks I'll have to catch them up online. But I see the YouTube channel is already set up for that, and I've managed to jump in and there once in a while. But it looks like a very fun meeting, and thank you, Marcus and Boumediene, for the invitation. So I'm Charles. I'm from Montreal, École de Technologie Supérieure. And yes, I've got some interests in algorithmic information theory. Today I'll be speaking about some result on the relationship between sophistication and busy beaver depth. So, oh, there we go. Okay, we've got algorithmic information theory high in our hearts. It obviously contrasts with the more conventional information theory of Shannon. And where it differs is really how it interprets the origin of data. So yeah, data in the Shannon philosophy, it comes from a random source. So we have stochasticity, probabilities, whereas in AIT, it comes from a computation. And I think it's a very strong point, especially with the relationship with the Church-Turing thesis, also interpreted by Deutsch, with making it all like a physical principle, where physical processes can be imitated arbitrarily well by computation. And the data that we collect in our hard disks and in our brain and so on all come, whether we like it or not, they come from physical processes. So to view the link between computation and physical processes, I think is a strong case for AIT. Now, I'm preaching for people who are already convinced, I'm sure, but it sets the background. Maybe we can say a few more things. If Shannon is rooted in probability theory, obviously AIT is rooted in computability theory, and the fruits might be conventional statistics as opposed to non-probabilistic statistics. So non-probabilistic statistics appears like a contradiction in terms, but it makes sense when we view the kind of statistics as model selection coming from the theory of programs and computability theory and AIT. So let me say a few more words about that, because sophistication is cast within the framework of non-probabilistic statistics. That's an image from Kolmogorov in the 70s where he explained his ideas. So we have a fixed data, call it X. X is an n-bit string. And think of X as a very interesting piece of data, like collections of countless experiments and so on. And we want to find a model for X. So in the realm of algorithmic statistics, a model for S is a set of strings of which X is an element. So that's very liberal. You know, we can define sets of strings in many ways. We just demand that X is an element. Now we have kind of opposing tendencies for quantifying good or bad models. So on the x-axis, I represent that we might want the model to be simple, or I write down K of S, the Kolmogorov complexity of the model. Shortest program that can spit out all the elements of S in some lexicographic ordering, the length of. And then we also have the cardinality of S. S could be a huge set, and then we might say, well, am I really well modeling X if S is a very large set? No, I would like S to be kind of a small cardinality to really identify X more properly. So I plot here log cardinality. It will become obvious why log. But then these are two opposing tendencies. And we can find canonical models. For example, that is a model per definition, 0, 1, n, the n-bit strings, right? It's a set. X is an element. It's a simple set. So its Kolmogorov complexity is very low because I specify it only by specifying n. So I need k of n bits to specify that set. However, it's a large set. Its log cardinality is n. And on the other end of the spectrum, I might consider this other canonical model, the singleton X. Well, that one has Kolmogorov complexity k of x, essentially, and log cardinality 0. So we find two extremes. And so this one could be called the underfitted model, and this one might be an overfitted model, because now I'm no longer having a model for X, I'm just giving you X itself. The intuition is that good models should explore trade-offs between being simple enough, but not repeating the incidental randomness or the boring noise that may reside in X. So what we do is consider all possible models, right? And they have a coordinate on that plane. And then I have that model, and having a plethora of possible models. Um, and so one interpretation is that from those models, we have a two-part code for X. The first part is to specify the model itself. And then once I have the model, I can just input the index or the lexicographic ordering of X within S. With that second part, then I can calculate X. Okay, and the idea is that the interesting properties of X should be residing in the model, and what we don't really care about modeling about X resides in the index. So of interest now becomes the boundary of this cloud of models, and this is known as Kolmogorov structure function. This one here, it's a model that has a sharp drop. So once we manage to specify the model that I called SM, it seems like we've captured interesting properties of X, right? Because we reduced by a lot. We had sufficient algorithmic information to reduce by a lot its cardinality. So we really specified X, and we did not spend so much bits of program into going into the incidental details about X, right? The models that are going along these lines are basically embedding some bits of index into the model, but we'd rather want to leave the bits of index outside the model. So in a way, the minimal sufficient statistics is kind of the interesting model that captures all the relevant properties of X, but does not start overfitting, right? That's the basic presentation of how algorithmic statistics work. Obviously, we're in the non-computability land, but we're happy to still make claims about what can be said. Now, this quantity here, namely the complexity of the minimal sufficient statistics, is defined as the sophistication of X, right? So it's interesting because it kind of measures how there is non-trivial patterns in X, right? If a string X is sophisticated, it means that I need a lot of bits of model to be able to say something non-trivial about it. That's the sophistication of X. Cool. So with a colleague, Geoffroy Bergeron, back in 2022, we had the idea of considering strings who may possibly admit multiple drops in their structure functions. And we tie these many drops to some notion of emergence, which is usually discussed more like high level in like physics paper / philosophy. But we thought we had a cute mathematical take on how to quantify emergence with the conjectured existence of such strings, right? At first, the sanity check would be to make sure that such strings, at least mathematically, exist, right? Does there exist any strings X with such a profile for its structure function? And by Vitani and Vereshchagin 2004, the answer is yes, there are, because basically all shapes are possible, like modulo logarithmic accuracy. And modulo, obviously, the constraints that like these kinds of shape must have slope at least -1 and so on. So all possible shapes are possible. Good. And then so with Geoffroy, we went after these models, right? Those models that are not necessarily the minimal sufficient statistics, but are progress on the way towards the minimal sufficient statistics. So I call them S1, S2, S3, and SM for the purpose here. And what could we say about these models? We call them minimal partial models because they look like the minimal sufficient statistics, but they're partial. They don't grasp the whole of the relevant information into X. And so one thing we could show is very intuitive and somewhat straightforward to show as well is that, well, the algorithmic information into S3 is basically contained into X. So from X and logarithmic advice, we can compute the minimal partial models. Right, sure. Okay, well, the minimal advice is, the logarithmic advice is necessary, but it's straightforward because we expect that S3 is not information about nothing, it's information about X, right? So now perhaps more interestingly is this one here, where we showed that the algorithmic information is nested, because that prima facie needed not be the case. For example, S1 might be some interesting patterns about X. S2 might have been some different interesting patterns about S. And perhaps S3 would have been the conjunction of the two. But it happens that no, in fact, S2 must embed the knowledge of S1. Okay. Yeah, now as Geoffroy and I are both interested in physics, so we thought that, running along the minimal partial models around these kind of jumps looked like an interesting take on the notion of coarse grainings, right? Because if you're given SM, you have the perfect theory of X. But then if you're imposed to have fewer bits of model, what do you do? Well, perhaps the best thing to do is to jump into a shallower model, a model of less complexity, S3 in this case, or S2. And so you're going into more coarse-grained theories or models of your string, right? And we identified the index part, the incidental randomness, with the boundary condition of a model. So, in physics, we have laws of motions which are extremely elegant, but we also need to specify the initial conditions, but that is usually taken for part of the boundary of the model, where it's just algorithmic noise, which is not really relevant. But now, in this view, we might also include something like the precise numerical value of friction coefficients, are coming into the boundary conditions when we're coarse graining. And if we have a more underlying theory where we can actually compute these values from more physics, then they're no longer boundary conditions. So what I'm saying here is that there might be parameters that are boundary conditions with respect to S3, but are not boundary conditions with respect to SM. I said boundary conditions. Even there, it's not exactly condition, boundary of the model. Cool. Now I'll jump to, the links with logical depth. So here I'll just do a small affine transformation here, right? On the y-axis, I was plotting log cardinality of S, which happened to be the length of the index, right? It's how many bits I need to specify the lexicographical ordering of X, because there was S, well, cardinality of S elements, I needed log cardinality of S bits to specify it. And then I can just consider instead the sum of the two. Okay, so I'm basically adding up also the x-axis, right, which was already the complexity of the model. On the y-axis, I have the complexity of the model plus log cardinality of S. So that's the length of the two-part code now. And we see that it will reach k of x here. Yeah, that's k of x. Yeah, that's the length of the two-part code, modal complexity. It's just an affine transformation. Why not? We still have sophistication that is at that value. Now, let's call that the description profile, and let's forget it for a little while. Now, there's another idea that came up from Bennett in the 80s, where he was also going after the non-trivial organization into a bit string X. But he had a very different take than the algorithmic statistics program, which was to consider not models or algorithmic models for X, but rather programs for X. There's multiple programs that can generate X on a universal Turing machine. And we can, assess two properties of these programs, their length and their running time. And we can plot it also in this fashion. But now bear in mind that the length will be, length of the program P, which will be a number is smaller than N. But the running time is, in general, will be an astronomical number, right? It's a huge values that running times can take. So to compare apples to apples, we will renormalize this axis in order to have values that are ranging in the same kind of range as 0 to n, where n is again the length of the string x. So that's the busy beaver inverse renormalization, basically, where you send the largest possible running time of an n-bit program back into n. Okay, so for example, we have the printx program. Okay, the printx program is it's quite long. It's n-bit long. Its length is n, but it's running fast. Especially on the busy beaver scale, it's ridiculously fast. So we have a dot here. On the other hand, we might have something like x star, the shortest program for x. It has length k of x. But in my example, I'm supposing that it has a running time that is fairly long. In fact, it would be yeah, it's non-trivial on the busy beaver scale, which is huge. Then I can consider the set of all such programs and realize a profile of this kind, right? And we can call this the time profile for the string x. So I consider the set of all programs that generate x, and I kind of, measure them by their length and by their busy beaver running time. And then here I've got, yeah, x star had busy beaver running time d, which meant that it was roughly running for as long as the longest running program of d bits. Right, we have plenty of programs of d bits. Some of them never halt. Forget those. Take those who halt and take the one that runs for the longest. That's busy beaver of d. Well, x star is, in this example, running on the same lines. Same order of magnitude of time. Okay. What amazed me was to find out that these two curves, the description profile coming from the algorithmic statistics and the time profile coming from the logical depth in the busy beaver regime, are in fact, the shapes coincide up to logarithmic resolution. Okay, I write this like that. That's logarithmic resolution. This curve, capital lambda of x, is roughly the same curve as matcal L of x, who's assessed by the running time. This was shown by Antunes, Bowens, Sauto, and Teixeira back in 2017. And yeah, I thought that it's a very interesting idea because there are apparently two unrelated ways of going after something deeper than just the Komorogov complexity. Something is kind of can be thought as the non-trivial organization into the string. And these two ways of doing it basically coincide. Okay, so one aspect that we can see from the time profile of X, so suppose we have X, which really does indeed have this kind of shape as a description and time profile. What we see from that is that X star contains a lot of information about the halting program, right? Because it runs for busy beaver of D. So it decides the halting program for all programs smaller than D. And so with a minimal advice, which is just k of x and x, we can get x star, and therefore we can get the running time of x star, and therefore we can decide the halting problem for programs smaller than D. So this guy contains halting information. Or another way to put it is that it can be used to compute a prefix of omega. Now, where we're going, so I thought, so when I saw those two things, I think my motivation, I think it's worth sharing it with you, is that I was always, like Marcus said this morning, he mentioned this relationship, which is the chain rule for algorithmic complexity. It's one of the triumph of AIT to have a chain rule, especially on the harder side of the proof. I thought now that we have these very fantastic measures, do they obey some kind of chain rule? Or do they obey some kind of algebraic relationship that could relate, say, the sophistication of xy with the sophistication of x and the sophistication of y given x? And same for the depth. So the first part was to make sure that we define the relative sophistication and the relative depth correctly. But it's fairly straightforward, right? If we have relative Komorogov complexity, we just assume we have the string z sitting on the tape. Let's assume we have a string z sitting on the tape. And so we have this string z sitting on the tape. We're looking after models for x, given that we already have z. So the complexity of the model given z. And that's how we can define the description profile for x given z. Okay, we still define it this way. And the same thing for the time profile. So we're looking after programs that can compute x, but they already have z sitting on the tape. Their running time might get longer because, they might use the non-trivial halting information in z to run for very long, alongside with p. Okay, so these are somewhat canonical ways of getting into the relative complexity profiles. Now, okay, here we are. So it's straightforward from the time profiles to realize that these curves follow. Well, the relationship among these curves follow. It's clear at the limit of infinite time because that's just the chain rule. Okay, so Kolmogorov complexity here of the when there's no time constraints, that's just the Kolmogorov complexity of the pair, conditional Kolmogorov complexity of X. But by leveraging this formula for time-bounded complexity, but in the busy beaver regime, we get that the curves add up to one another. Right. And so we found already a first relationship between the depth of the pair and the depth of X and the relative depth of Y given X, which is that the depth of the pair, that is when this thing stabilizes to the line, must be the maximum of these two stabilization. I'm proving it with the graph because the curves add up. And so if this stabilizes, this is the sum of the two curves. Therefore, the two must have stabilized. So it will stabilize whenever the last one has stabilized. Okay. But now if we look at that was for the time profile, so the logical depth paradigm. Now for the algorithmic statistics and sophistication paradigm, yeah, we have this relationship from the work I cited earlier. We have that relationship. But now we find that when we look at the conditional profiles, they do not coincide. So lambda of y given x and L of y given x do not coincide. There's a gap between the two. And the gap is quantified as follows. So if this is coordinate I lambda is on my description profile, I prime lambda is on my time profile, well then I prime is related to I in the following way. I prime is the largest prefix of omega that can be computed from x and I bits of advice. Okay, so if x has no information at all about the halting problem, well then the largest prefix of omega that you can compute with I bits of advice is basically I bits of omega. So I prime and I would coincide when there's no halting information about x. But maybe x contains, in a non-straightforward way, halting information. For example, it could have like the even bits of omega. And so with I bits of advice, you can get 2I far, right? Because you can leverage the even bits of omega to compute a larger prefix of omega. So that's what quantifies the gap between the two measures. And therefore, from this function, I gave it a name, and that formula, we can also get a relationship between the sophistication of a pair of strings and the sophistication of x with the sophistication of y given x. Okay, 6 minutes left. I'd like to give a few minutes for questions, but maybe just finish with some thoughts on epistemology, like how do we build knowledge? I think that's a big motivator for our community. On the non-probabilistic side of things, it may look like something like this, right? Scientific data X always increase. We keep on gathering data. We look at anomalous parts of our theories, and we invest and make particles collide in that regime where we find that there might be puzzles. So X always increase. The truth is that we don't run like a dovetail kind of program to find scientific theories. That's not how it works. We just conjecture them, right? What if space-time bends? What if we have a Hilbert space to describe particles, and so on. But we conjecture models that can better explain X. And then better models arise, and models can be proven false when we have a contradicting piece of evidence. So, right, if we have a scientific theory, it constrains our set of possible strings that we ought to measure, but then we find that X, as it increases, contradicts that. We're falsifying theories this way. Or we also sometimes discard theories on purely theoretical grounds. Like we found a better fit model or a more unifying paradigm. And so scientific investigation may be identified with, at least in the AIT sense, with the upper semi-computation of the structure function of our observations. So, but yeah, the upper semi-computation done in a non-systematic way. We're not really running a program forever. We're we're coming up with guesses and try to put our guesses down. Now, however, theories are never proven right, nor optimal, nor final, which is a property of upper semi-computations or semi-computations in general. And that's very in line with fallibilism, right? Even if we find the unified theory of gravity and quantum, we won't have a certificate that tells us that that's true. So even if we stumble on truth, there's no final flag that raises. We'll just keep on looking for errors. So I'm curious, maybe that opens for discussion on how this epistemological take with non-probabilistic statistics relates with the Solomonov program and universal AI program of induction, and maybe also bring up the fact that is data really fundamental in our scientific investigation, given that, after all, when we look at the data that's collected in the latest experiments, they're all very much theory laden, right? Even if we look at data from the medical sciences and we have like glucose levels, to even make sense of those numbers, we need a theory about what glucose is in the first place. So there's this interplay between our theory making and our understandability of data, which, well, it's subject for discussion. I think it's a good place to stop.